Okay, let's begin. We're going to start a topic on waves. Let's start by looking at vibrations first of all. So a simple vibrating object would be something like a pendulum or something at the end of a string here. So you've got it vibrating backwards and forwards. So that pendulum will have a frequency first of all, which is how frequently it vibrates. So the way of defining that is how many vibrations it does per second. So if you do it like that, it does quite a few vibrations in a second there, so it may be, say, 2 or 3 vibes per second. So they talk about having, say, 2 or 3 hertz there as the number of vibrations per second. So when you're doing that there, you could say the frequency here, you might be doing 2 vibrations per second, 2 vibes per second. And so that's a frequency of 2 hertz. All right? But obviously you can do 3 hertz, 4 hertz, 5 hertz. So here when we've got a longer string here, you'll find the vibrations are not as fast as that. So we sort of count this and go 1 and 2 and 3 and 4. So you could argue it's doing roughly 1 vibration per second there, which means the frequency of that one would only be 1 hertz. Okay, 1 vibe per second. So frequency is how frequently it vibrates, and you've got to bear that in mind. The tuning fork here that we've got, that actually vibrates at 256 times per second. It's got 256 hertz on it. So you can hear that. That's what that sort of pitch of that note sounds like, 256 times per second, 256 hertz. So these prongs are going backwards and forwards 256 times every single second. Now, there's another thing involved with this here, it's also the period of the wave, and the period's got a symbol T, that's the period. Now, period normally involves some sort of a time. When they talk about periods, they talk about time period. So it's normally measured in seconds, but so you might have a period of time that takes, say, 2 seconds, and that's the time it takes for one complete vibration or one complete cycle. So the period of the moon would be like a month, 28 days roughly, and that's the time it takes to go around once. In the case of this one here, the question would be, how long does it take to go back and forward once? Okay, so that's the period there. So if you think about it, when we had it back up here and the frequency was 2 hertz, 2 times per second, the time for only one full swing backwards and forward would only be 1/2 of a second though. Okay, because if the frequency was 2 up there, if the frequency was 2 hertz, we expect the period to only be 1/2 of a second, like that. Similarly, if you had a frequency that was going backwards and forwards 10 times per second, 10 hertz, so it's got a frequency of 10 hertz, so it's really fast there, it would only take 1/10 of a second to complete one full cycle. If it was 50 hertz, it'd only take 1/50 of a second to complete a cycle. So the period and the frequency are directly linked there. 10 hertz for a frequency would mean only 1/10 of a second for the actual period for one. So the relationship here is that frequency is reciprocal to the period, or period is a reciprocal to the frequency. It works both ways around. When you hit that with an object, you're going to get a lower pitch note there. It goes higher. So the shorter objects here, it turns out, vibrate with a higher frequency. The particles inside vibrate at a faster rate, at a higher frequency there. So there's a variation of notes there. So same with tuning forks really. If you look at those two tuning forks there, the shorter one will actually have the higher pitch note. This is the 512, and this is the 256. So they're both Cs, but one's an octave different to the other. All right. So it turns out that the source of all waves is actually a vibrating object. Okay. So to have a wave going past, you need the vibrating source to start with, but then you need some sort of a medium to carry that energy away. So in the case of say sound, you can have a vibrating source that might be just something like this. Okay. There's the vibrating source there. The air around it, those particles get hit by that vibrating source. The particles bump into each other, and there's a set of compressions that's sent through the air and across the room, and that's why you're getting a wave, in this case a sound wave. If you change the length of this, you can get it to vibrate more frequently at a higher frequency and a higher pitch. So the pitch and the frequency are linked together. Okay, so let's just have a look at that for a second in terms of a recap. If you look at these notes here, key points here would be that a vibration, first of all, which we didn't really define, was any backwards and forwards motion, or to and fro motion, or up and down motion, but they normally describe it as a to and fro motion. So a vibration is a repeating to and fro motion. Okay, it's got a couple of properties. The first of all is the frequency, which is how often it vibrates per second, number of vibrations per second, and that's measured in hertz. So for example, if it did 20 vibrations in 4 seconds, we'd expect that to be 20 divided by 4. We're averaging 5 per second, so the frequency would be 5 hertz for that. Now, a tuning fork that low you wouldn't hear, but a typical tuning fork of 256 you would hear, like we just sort of showed you. Okay. If you look at some other ones further down here, the period is the other very key thing to keep in mind. That's the time for one full swing, measured in seconds normally. So if it does 5 vibrations per second there, like we're saying here, we expect the actual time period to be just 1/5 of a second or 0.2 of a second. And that's a relationship. But you can actually rearrange it to find frequency as well. To get that vibration going as some sort of a wave, we need the vibrating source, yes, but we also need some sort of a medium to carry those particle energies away. So it would be air. Does water do it? Yes, it actually does better in water, in fact, in terms of how far it will go and how fast. And solids do it even better again because the particles are closer together. So this is a way of transferring energy without transferring any matter the wave does. So there's a couple of types of waves you can look at. We just look one here. They're hard to do with any one person. We'll try it out. So if you take a slinky spring here and you make a vibration with the slinky spring at one coil there, and you can just send a finger pulse down like that, you can see that the slinky spring is connected all the way down the coils. The energy gets passed on from the first vibration to all the other coils, but they end up coming back into their original position. So the energy is passed on without the matter going from one end to the other. So this is a way of transferring energy without transferring matter. So this sort of wave here where the vibrations are at 90 degrees to where the wave is going are called transverse waves. The transverse basically means across, so the vibrations are across ways to the wave velocity. Like that. Okay, that's a typical transverse wave. So that actually might be the case. That's the sort of case you'll get across the surface of water, for example. There's another way you can do it, and that's where the particles bump into the back of each other, like this. What you should see heading down there is compressions going down there and expanded areas where it's spread out. So because the vibrations are this way, and that's the same way as the wave is going, along the same direction, it's called a longitudinal wave. It's along the same direction. So there are two key types of waves: longitudinal waves and transverse waves. They're quite hard to draw them. It's fairly hard to draw those waves, but we can actually try to do some. So if you do the transverse wave here, transverse spell. With the transverse wave, we could just draw it like this. Okay, and I'll just draw a dotted line there to represent the starting position there, the rest position. So with those there, there's some key parts to that wave. First of all, it's got a top of a wave, which is called the crest of a wave, which they surf on, like we'll talk about that. The trough of the wave here is like the horse's trough or pig's trough. That's the base here. So that will be the trough of the wave there. Drop down there. This sort of dotted line you can call the rest position, but people don't talk about that as much these days. And then you've got the amplitude, which is the maximum distance it moves out, up or back. So there's an amplitude there, there's an amplitude there. It's the maximum displacement really from the starting position there. But let's say it's there. Now the length of the wave itself, you can measure from the crest to the next crest as a wavelength, or you could go from trough to the next trough as a wavelength, or any position where you end up going through a full cycle and ending up at the next sort of point of the full cycle. So for the wavelength, we can use a Greek letter L, which is lambda, to represent the wavelength, or length. So it's spelled lambda, right? But that basically just means the length of the wavelength. So that's the wavelength, and it's measured in meters. Just like the amplitude is also measured in meters. Over here. Right, for this particular diagram. So this is a transverse wave. So what we're saying here is the vibrations are going to be 90 degrees to the way the wave velocity goes. That's the way the vibes are going. And they're the key parts of that wave. Okay? If you look at the other wave types there, the longitudinal wave one that we've talked about already, the longitudinal wave has its vibrations going in the same direction as the way the wave's going. Now that's a lot harder to actually draw, so we often draw them as, that's why the wave is going there. So there's the vibes, there's your wave velocity there. Whereas here's your vibes at 90 degrees, wave velocity is that way at 90 degrees. So here we've got a longitudinal wave. You can draw it as a series of compressed areas where the slinky spring was sort of compressed together and some spread out areas, and I've exaggerated this a bit. So a series of compressions and expansions where the pressure is sort of high and low. So the compressed areas where the pressure is high, the expanded areas where the pressure is lower. And so you'll get that sort of a picture, that's how a sand wave would go. You can picture this as dominoes bumping into each other and then resetting themselves each time, but they end up passing the energy down all the way along the actual motion there. Okay. The other way you can see this is to use something like a wave machine here, something like that. Bring that in closer there, and you can see these are going to go up and down at 90 degrees the way the wave is going there. Whereas on the end here, this one here, you should be able to see this is a compression that's going to go down in the same direction as the wave goes. So the wave's going downwards, and the compression and the expansion should be moving in that same sort of line of direction as well. So what we're now saying is that there's two main types of waves. Your transverse wave, the vibration is at 90 degrees to wave velocity. On the transverse wave you've got some certain parts there. The vibrations are going to be 90 degrees to velocity, but you've got a crest, you've got a trough, you've got a wavelength, you've got an amplitude. They're all coming from that rest position. If you look further on, you can also do a longitudinal wave here, where the vibrations are the same direction as the wave velocity, and you can normally indicate that with some compressions and some expansions. Okay? But the vibes are in the same direction as the wave velocity, as you can see here. The wavelength for a compressional wave, the longitudinal wave here, would be the distance between a compression there and the next compression, or it could be between an expansion and the next expansion as well. That would also work, but that's the wavelength there. So they're the key parts of the waves. Other things to consider, apart from that, you've got a wavelength there, then we've got to consider with waves, how long the wave is between parts of the cycle there, so how long that distance is there. You can talk about the frequency of the wave and the period of the wave, and we can also talk about the velocity of the wave, how fast it's going. Now it turns out the velocity is linked to the wave by this formula, the wave equation. Frequency times by wavelength. So the wave equation can be used to calculate any one of these things given the other two. So in the case of something like this, if you actually knew the speed of a wave, so let's say we know the speed of sound to be 340 metres a second, so that V stands for velocity actually, but velocity, speed, the same thing here in terms of the size of it. And the wavelength here is what we don't know for the wave. But if we were to use our tuning fork that I've just shown you before of 256 Hertz, you could use this formula to work out the unknown wavelength. So if you want to solve for that, we can work out the wavelength here, velocity over frequency. You can do 340 metres a second over 256, and you end up with about 1.33 metres. Okay, but you could have actually found the velocity if you've been told the frequency and the wavelength, or equally, you could have actually found the frequency if they told you the velocity and the wavelength. So that formula works in any of those sort of combinations, and obviously those properties are pretty significant for waves, so that's a pretty important wave equation to be able to use.